right, good morning, good afternoon, good evening, depending on when you're watching this. Hope you guys are doing well out there. It's been a while since I've seen you. Hope you're adjusting well to overall our campus moving to online format. So it's been a while for me to make these videos, but I'm just trying to get the format right down. So I want to be able to provide you with the more detailed work, and then of course you're going to answer some responses from the handout. So I'll still send out the handouts as usual, and I will provide some videos to walk you through them, and then excuse me, and then we'll work through them. Okay, but so I wanted to work on a problem from the curve sketching example here. So I just want to walk you through how we work through these and how we're thinking through these problems and for one of these examples. So here I'm focusing on the function f of x, which is 1 over 1 plus e to the negative x here. Okay, so here we're dealing with this function here. So as far as the domain goes, well, I mean, we want to look into, well, we know exponential function has a domain of all real numbers, right? And now we just kind of have this rational version of it. But remember, e to the negative x is it's never negative value, and it's always greater than 0 here. So as far as domain, we're going to have all real numbers here. Okay, our range here is from 0 to 1, and where I get that from is, well, this value here, e to the negative x, it ranges from 0 to infinity. So when it's 0, we get 1 over 1 more or less, and when it's infinity, we're getting 1 over 0. So my range is from 0 to 1. And of course here, 0 is a horizontal asymptote for this function, so that's why I have my open brackets here. And down here, from a y-intercept, x is equal to 0, so I could easily plug that in. I get 0 here, and I will get not that number exactly. I will get fix that there. Okay, I will get 1/2. Okay, and so as far as my x-intercepts, I won't have any, and my vertical asymptotes, I won't have any. And as far as my horizontal asymptotes go, and this can maybe help you with the range as well, as I take the limit of my function as it goes to negative infinity. Well, this is going to go to infinity, so therefore this is going to go to 0. And as this goes to infinity, this is going to go to 0, therefore this is going to go to 1. Okay, so therefore I have my vertical, horizontal asymptotes lined up. Now, for my next step, I want to take the derivative of the function. So here I will use the quotient rule. So what I have in green here is where I take the derivative of the function. So the green part is this is my bottom derivative top minus top derivative bottom. So just to keep track of notation here. Okay, and then all over the bottom squared. So this derivative function we want to set equal to 0, and the reason is we want to find critical points and mostly where our function is increasing or decreasing, right? Because we want to sketch this graph. So if you just focus on the numerator portion, we get e to the negative x is equal to 0, which is no solution. And the common mistake there is, I mean, if you weren't familiar with this function, you may try to take the natural logarithm of both sides to solve for this. And so if you did that, you would get negative x is equal to natural log of 0. And remember, natural log of 0 is undefined. Remember, the log function approaches negative infinity as x values approach 0, but it's undefined at 0. So be careful there. It's a common mistake that we made. But just note that even though we didn't find any critical points, this derivative function here is always going to be greater than 0, because e to the negative x is greater than 0, and obviously what we have in the denominator is always going to be greater than 0 here. Okay, so therefore f of x is increasing over its interval. Okay, the next order of business is a second order derivative, and so we want to find where our function is concave up or concave down. So from this original function, I just apply the quotient rule again. Now these things may look intimidating, but remember, we need to factor as much as we can to make problems easier. Okay, do not try to multiply everything out. That's just a dead end. Okay, but so here I'm doing, once again, green, I'm doing bottom derivative of the top minus top derivative of the bottom. So keep track here. I'm using the chain rule to get this result here, because this is really e to the negative 1 times x. So my outer function is e to the x, and my inner function is at negative 1 times x. Okay, and of course here I'm using my chain rule. Okay, I'm bringing my 2 down. I'm using power rule in here. Evaluate the inner times derivative of the inner here. Okay, so once I'm here, I definitely do not want to multiply these things out because I know I'm going to set it equal to 0 and solve for x. So the trick is to factor. So what I see here is that they share a factor of negative e to the negative x in these terms, and they share a factor of 1 plus e to the negative x in both terms here. So in purple here, these are the factors that I've taken out from each of these terms before and after the minus sign. So sorry, that keeps popping up. Before and after the minus sign. Okay, and so and then what's left is this 1 plus e to the negative x. And what's left in this term is just the minus 2 e to the minus x. That's all that's left after I factor them out. So of course I'm going to set them equal to 0 in hopes to find inflection points and where f of x is concave up and concave down. Okay, so once again, I'm just going to focus on the numerator here. Just focus on what's in the numerator here. And so what we get is these three products here. Okay, so these 3 factors here. So pretty much what we do with zero factor property, we set each of them equal to 0 and we solve for x. And what we notice in the first 2, it's impossible for these to be 0. Okay, either negative x is always greater than 0. This is always going to be below 0 regardless, and this is always going to be above 0 regardless. We're going to have 1 plus a constant, a positive number. But here we could solve for this here, because if I continue forward, this is just e to the negative x equal to 1. If we take natural log of both sides, I'll get negative x equal natural log of 1. Therefore, x is equal to 0. Okay, so now I'll leave it up to you to determine where the function is concave up and concave down by checking for test points. And then I want you to go ahead and graph. And just when you're at home, I encourage you to use Desmos so that you know the result that we're getting here. And if you look at Desmos, this is my function here. So as you can see here in my function, we see that it's more or less increasing over its entire interval. Okay, so that's where we get f prime of x is bigger than 0. But the issue we have here is so here we have my y-intercept, of course, at 0.5. But what we have here, as far as from here to here, we see that it's concave up, right? We see that it's kind of curve bending up, right? And then from here to here, we see that it's concave down. Okay, concave down. So we see that shift in concavity here. And there's my y-intercept, and then of course, you know, if I want to sketch these lines, like if you want to sketch your horizontal asymptotes, you can say, well, y is equal to 0. Oops, sorry. Let's just say g. Maybe I could do g of x is equal to 0. G of x is equal to 0. Okay. Equal to 0. There we go. And we could say here t of x is equal to 1, let's say. So you can kind of see your horizontal asymptotes if you want. You can put dotted light, you know, you could go here and you could pick, you know, you could put your style there if you want to look more like an asymptote, you know, if you want to make it look different there, we can do that. Okay, but anyway, so I mean, use Desmos when you're home to help guide you there. But I hope this video was helpful. I'm trying to keep them short and sweet. I know attention spans can be even shorter when we're looking at online content, but hope you enjoyed, and I plan on making another example for you. But I hope you guys are doing all right, and we'll see you soon. Bye.